Okay, so in this video we will be looking at rates of change. Okay, we're just going to head straight into an example and that will help best describe what rates of change probably are. So, example 1, air is blown into a spherical balloon at a rate of 160 centimeters cubed per second. We want to find the rate of increase of the radius when the radius starts initially at 5 centimeters. Okay, so rates of change is when we want to work out if something else is increasing, then due to that, what is possibly the rate of change in something else? Okay, would something else increase, decrease, stay the same? How can we get an expression, a mathematical formula to work that out? Okay, so let's try and work out this question. Okay, we've been asked to find the rate of increase that the radius will have. Okay, when we know that the radius initially was 5 centimeters and that 160 centimeters cubed of air is getting blown in every second. Okay, so the volume is increasing. Okay, so what we know, okay, is that we know the volume formula for a sphere is 4 cubed pi r cubed. Okay, that's a formula that we've seen even during National 5. We know the volume is changing due to time. Okay, so as time is going on, the volume is changing. It's 160 centimeters cubed per second. So the rate of change that the volume has, okay, so the differential of volume with respect to time, okay, the rate of change is 160. Okay, so that's going to be part of our data. And we know that the radius is initially 5 centimeters. Okay, what we want to work out is the rate of change that the radius has. Okay, so dr by dt. Okay, that's what we mean by rate of change, or the rate of increase, because it'll be increasing up, that the radius will have. Now what this means is that the radius isn't just a natural number and it's not going to stay at 5 centimeters at a time. The radius will also depend on time, so it's a function of t as well. Okay, so the volume is a function of t. Okay, the volume changes with time and so does the radius. Okay, the more air is blown into this balloon, the volume increases due to the amount of time it's done that, and also the radius does as well. Okay, so they're both functions of t, which is very important. So solution. Okay, what we're going to do is, okay, we're going to use implicit differentiation and differentiate everything with respect to time, okay, because we want to get dv by dt, dr by dt, okay, we want to differentiate everything with respect to time, okay, so that's what d by dt means there. Okay, so we're going to do implicit differentiation and we're going to use it on this formula that we know for the volume of a sphere, because the volume is going to change, so the rate of change, we'll use the original volume formula to do that with us. So what we do for implicit differentiation is we differentiate just one part at a time. So if I differentiate v, I need to remember v is a function of time, then I'm going to get, start with that formula there, okay, I'm going to get dv by dt on the left hand side. So v differentiates to dv by dt, okay, that changes with time. So if I differentiate it, it's to respect to time, dt. Well, 4 over 3, sorry, pi is a constant, okay, that's not something that respects the time, so that's going to stay the same. I just need to differentiate r, but I need to remember r is also a function of time. So if I differentiate using the chain rule, okay, well I differentiate r normally, so the 3 comes down, multiplies as 4 over 3, that gives me 4 there. I take 1 off the power, that'll be a power 2, so it'll be 4 times pi r squared, which is what I've got there. But then I need to remember, I need to multiply that by the differential of r, which is dr by dt. Okay, so my rate of change for r there. Okay, so that there differentiates using the chain rule to that there. Okay, just quick recap. That 3 comes down, multiplies that 4 over 3, that gives me 4. Pi stays there as a constant, so pi is there. I'll reduce the power, okay, so it becomes r squared. I need to remember to multiply by the differential of r, which is dr by dt. Now I want to get dr by dt, so I need to rearrange this in order to do that. Okay, so if I rearrange that, okay, dr by dt is going to be equal to 1 over 4 pi r squared times dv by dt. Okay, right, I want to get a value for this, so I now can put in my formula, my data, sorry. So I knew the rate of change for the volume, okay, was 160 centimeters cubed per second, so I'm going to put 160 into there for dv by dt. And I know that r initially was 5 centimeters, so that's going to go into there. Okay, once I substitute that in, okay, I get the answer 0.51 centimeters per second. So the radius is increasing of a size of 0.51 centimeters per second. Okay, that's the rate of change for the radius. Okay, now that has got a physical example, and most examples on rates of change are physical examples. Okay, Therefore, you'll need to use data that we know previously. We had to use the volume formula. Okay, you'll see in the next example we'll have to use a different formula to get us started, but that's what a lot of these questions revolve around. Okay, however, the process is we differentiate implicitly to get our rates of change into our formula, rearrange to get what we are asked for. Okay, and we use the data to help us with that. Okay, let's look at the second example. So, example 2, a cylinder of radius r and height h is closed at both ends. It says its total surface area is 15 units squared. We want to find an expression for dr by dh. Okay, so that means there we want to work out the change in radius with respect to the change in height. Okay, that's what we are doing there. We're differentiating with respect to height. So what this is basically meaning is that we have a cylinder closed at both ends. Okay, we know the volume, or the surface area is fixed at 15 units squared. So if we change the height, how does that affect the radius in order to keep the same surface area of 15 units? Okay, that's what we are thinking about in this physical example. Let's see if we can work out how to do so. Okay, well, solution. So the surface area of a cylinder once it's closed at both ends, okay, well, it's 2 pi r squared. Okay, so the area of the top part and the bottom part is pi r squared because it's both of them. We have two lots of pi r squared. Then we also have to add in the height aspect of the cylinder. Okay, so we times the circumference by the height. The circumference is 2 pi r times by the height h, so it's 2 pi r h there. Okay, so this here, okay, is the area formula for a surface area of a cylinder that's closed at both ends. Right, let's see what we know. Okay, well, we know that the area is 15 units squared. That's what we know from my data. Okay, I also need to remember that the radius will be dependent on the height here. So if the height changes, that impacts on my radius. Okay, so the radius will be a function dependent on the height h here. Okay, so it's a function of h. So when we differentiate this, we'll have to differentiate this implicitly. I need to remember that if I differentiate the r aspect, I need to remember it's actually a function of h as well. Right, okay, so let's differentiate this implicitly now. So what we're going to do is we are going to have to differentiate each aspect with the terms of h here. So if I differentiate this first part, so if I differentiate 2 pi r squared, well, we treat it like the chain rule. So what we do is we differentiate with respect to r, so the 2 comes down, so that'll be 4 pi r. Then to remember, because I'm differentiating r with respect to h, and it's a function of h, I have a dr by dh attached to it. So I multiply by dr by dh. Okay, so when I differentiate this, I'm going to get this coming out the other end. Okay, I'm going to look at the second function now, which is 2 pi r h. Now that is actually a product rule, okay, because I'm going to differentiate. I need to differentiate both parts individually and multiply them against each other. So I've got the 2 pi r function hitting the h function there, so it's a product rule. Okay, so if I just scroll down a little bit more, you can hopefully see that now. So I'll let u be my h function, okay, and if I differentiate u with respect to h, okay, if I differentiate h, I get a 1. I'm then going to have to differentiate this with respect to h, so I'm differentiating r, but remembering I need to multiply by dr by dh then. So if I differentiate that by r, the r disappears, so 2 pi, right, remember to multiply by dr by dh, okay. So using the product rule, okay, uv dash, so it's going to be h times 2 pi dr by dh, so I've got 2 pi h dr by dh there, plus vu dash, so it's 2 pi r times 1, which is just 2 pi r. So that's what the product rule will give me there. So when I differentiate the second part here, I'm going to get that coming out there. If I differentiate 15, okay, that goes to 0. So putting this all together, okay, I get this coming out here. So once I differentiate that, this is what I've got here. Now we want dr by dh, so I'm going to move the 2 pi r over to the other side. It doesn't depend on dr by dh. I'm going to take a common factor dr by dh out of these two terms here, and I'm then going to get dr by dh on its own by dividing by this bracket. So this goes on the bottom, and we can just simplify by dividing everything by 2 pi. So if I take off 2 pi on that, I've got an r, divide that by 2 pi, okay, that 4 becomes a 2, so I've got 2r, plus divide that by 2 pi, I get h there. And that is what an expression would be on the rate of change of the radius defined on the change in height. Okay, so there's two examples on rates of change. Again, very physical examples. However, implicit differentiation is the key in order to solve these questions here. Okay, and remember, you'll have a lot of chain rule and possibly product rules when dealing with this as well. Okay, thank you.